All right, so this is going to be a very detailed explanation of this problem we did in class 8 with the nozzle. So we have a nozzle with two entrances. We have water flowing in entrance A, inlet A, and water flowing in inlet B. We were told that the angle between A and B was pi over 3 radians. And we know that the x-axis is lined up with the flow at inlet A here. So the question was, how do we find the force to hold that nozzle in place? And that's what we're going to do. We have the diameters of all three of the orifices, 2 inlets and 1 outlet. And the water is flowing steadily through this nozzle, as it typically would. So what do we do? How do we solve such a problem? Well, this is a force. We're being asked for a force. So that should make you think of the momentum equations. And if you look at we're doing control volume analysis. So this is a control volume analysis momentum problem. And we want to find, say, this force F. Force, of course, is going to be a vector. In this case, it clearly is going to have two components. There's water coming up from in the z direction here. So we're expecting that there's going to be an x force and a z force. There will be no y force. There's no y velocity in any of these inlets or outlets. So we can assume that the y force will be 0. And we'll see that that will play out here. If we had a y term, it wouldn't show up anywhere. Anyway, it would come down to 0. But we need to worry about the x force and the z force here. So this is the equation that you should be looking to. These are the x and y and z force equations using control volume momentum conservation. So that's control volume momentum conservation here. And these are the autofocus there. These are the x force and the z force. And so we have two terms in each of these force equations. And the two terms consist of the time rate of change of the momentum in the control volume for both x with u velocity and w with the z velocity. And then these terms, which represent the amount of momentum being carried in and out of the control volume by the moving fluids. And these two terms here are 0 because it's steady flow. So this is a time rate of change. That's what the d by dt means. And if there's no change in time, then this term is going to go to 0. And that's true of this nozzle. The flow is happening. You turn it on. It's steady. The flow is continuing. Nothing is changing in time. The velocity is changing from the inlet to the outlet of the nozzle. But that's not a change in time for the nozzle. The nozzle has the same velocity at every position over time as long as it remains on as we've described it. So these two time-dependent terms are 0. So you're really focusing entirely on these right here. These two terms are almost always going to be the important terms for momentum conservation in problems that we study, basically. Usually the systems are, in fact, steadily operating, steadily flying, steadily moving, whatever they're doing. So this is the steady term that'll give us a force. So we need to analyze these terms to see if we can figure out what the values are for them. So we'll break those out because we have inlets and outlets. So notice that this only applies when you have fluid that's going to go through the control volume surface. So we talked about this in the lecture videos, that if you have an impermeable surface like the edge of the nozzle, you don't have to worry about this. So you're not going to integrate here or here because there's no fluid entering or leaving. It only matters where things are entering or leaving because that's the only place where u dot n is going to be non-zero. U is 0, of course, all along these impermeable surfaces that don't have any inlet flow or outlet flow. There's no u there, so that u dot n is going to be 0. So these terms are only going to be non-zero where there's either fluid entering or leaving the system. So that's what we're concerned about. Surface A, surface B, and the outlet surface. Those three surfaces have fluid entering and leaving. So this term will be non-zero on those surfaces because the u is not 0 as it goes, and you're supposed to be integrating all around the surface. So if you're on a part of the surface where u is 0, it just doesn't matter because u is 0. So 0 contribution there. Only worried about the places where there's non-zero u on these surfaces. Remember, u here refers to velocity in its entirety. That means x velocity, y velocity, and z velocity. This only refers to the x velocity, because remember, u is made up of u is equal to u, v, and w. That is x velocity, y velocity, and z velocity. So this is zero velocity here on the surface. It's zero in all directions. The whole thing is zero. All right, so no worries there. 3 surfaces we have to consider. So we break this out into those 3 surfaces and try to do these integrals, right? So here they are for the 3 surfaces: surface A, surface B, and surface out. Those are the inlets, A and B, and the outlet. So here are these same integrals, just written for those surfaces. So we have u dot n, this is the velocity dotted with the outward facing unit normal, integrated over surface A. U again, because we're in the x velocity term here. X velocity here gives you a u here, a little u with no vector. This is the x velocity. The x velocity times the rho times u dot n again. Surface, this is the area of surface B. And finally, the outlet. Again, x velocity, rho, u dot n, outward normal, velocity at that outlet surface, integrated over the area of the outlet. For the z, we have the same thing, but now we have w here because this is the z velocity, z velocity, z velocity, but we still have u dot n. So this is the amount of fluid that's passing through the surface. So it's not, there can be there's a z velocity, but the amount of fluid that passes through the surface depends on the entire u velocity, not just the z component of that. This is the momentum piece. Z velocity times rho is going to give you a momentum in z, but this is the amount of fluid that's being carried into or out of the control volume by that fluid moving. So this is the amount of fluid going through surface A, surface B, or surface out here, and this is the z momentum that is being carried in and out of that surface. All right, well, if you look at our nozzle back here, you see that there's a w component of velocity here, definitely. We haven't calculated what it is, but it clearly has an upward component to it. But the A surface and at the outlet, the velocity is not going up or down. It's just going purely in the x direction. So w equals 0 at A and w equals 0 at outlet. W equals 0 at surface A because there's only an x velocity. And w equals 0 at the outlet because there's only an x velocity there. So there's going to be no w here, and there's going to be no w here. So when we look at these two terms, they have w's in them for surface A and w in them for surface outlet. Sorry, you can't quite see that. So those terms are going to go to 0 because there's a 0 here and there's a 0 here. This one is not 0. So the only one that's going to stick around is the one that has no 0. But before we get to that, we're going to focus a little on the other term here, the u dot n term. What are we going to do with these? How do we calculate them? Now, a dot product is something you can just calculate. It's u dot n. So we know how to do dot products from Calc 3, and so you could calculate u dot n here. But there's a simple rule for the case where the flow is either directly going in or directly going out of a surface. That is, if the flow is perpendicular to the surface. So the flow is perpendicular to the surface. That means the outward facing normal is either pointing exactly the same direction as the velocity, or it's pointing in exactly the opposite direction of the velocity. That's what makes it perpendicular to the surface. So if it's perpendicular to the surface, then the value of u dot n here takes on one of only 2 values. It either takes on plus or minus the magnitude of the velocity. So this is obviously a very good, easy thing it's a shortcut essentially. You could calculate all this by using the actual normals, but if you know that the flow is perpendicular to the surface, which it definitely is for our nozzle. We've got the nozzle, we've got the flow coming in perpendicular to that surface A, perpendicular to that surface at surface B, and perpendicular to the surface when it's leaving surface outlet there. They're all perpendicular to the entries and the exits, which is typical of pipe flow. So if you have a perpendicular situation, then you know that it can only be the plus or the minus of the magnitude of U. So this is easier to calculate. So it's plus magnitude of U if the U vector and the N hat vector point in the same direction. That is, if U velocity, it's like this at the outlet. The outward facing unit normal points there. That's your outward facing unit normal. And your velocity points in exactly the same direction. They're pointed the same way. So that's going to give you a plus magnitude of U. It's negative of the magnitude of U if U and N point in the opposite directions, which would be the situation here. That's your outward facing unit normal, and your U vector is pointing directly into that. So that would be your opposite situation, and you have a negative magnitude of U for that. Can I prove to you that this is true? I can't exactly prove it, but I can demonstrate it. So here's an example. It's actually an example, not a proof, but it'll sort of show it to you. Here's I made this up. This is just some velocity, not related to this problem. 3, -1, and 2. That points in some direction, three-dimensional. This is the normal vector that points in the opposite direction of this. How do you know this is a normal vector? Well, you could calculate it. You could figure out its magnitude. A normal vector has a magnitude of 1. If you calculate this magnitude, you will find that it is 1. So we're going to dot U dot N, and we're going to see what we get here. U dot N, here's your dot product. First element times x plus y element times y element plus z element times z element. That gives you your dot product. So when I do the dot product, I get negative point. You take all these numbers, add them all up, and you get negative 3.7417. That's my dot product. I have claimed that if they're pointing in the opposite direction, the dot product should be the negative of the magnitude. So I need to calculate the magnitude of the U vector. The U vector magnitude is 3 squared minus 1 squared plus 2 squared. Take the square root, 3.7417. So it works exactly, of course. Math works. So the U dot N is negative 3.7417, and the magnitude of U is 3.7417. So we see, at least in this example, that when the U vector and the N vector are pointed in opposite directions, the dot product of U dot N is in fact just the negative of the magnitude. So what would you do if N and U were not pointing exactly in the same direction or exactly opposite each other? What could you do then? You would have to calculate the dot product. Is that impossible? Absolutely not. You would have to be, somehow told what the orientation of the surface is. You would have to figure out what the N hat is that represents that surface, an outward facing normal, and then you would take the dot product with whatever the U vector is, and that would give you the amount of fluid passing through that surface. But in many, I would say, a huge majority of the problems that you're going to be dealing with in this class, and really in most engineering applications, it is often the case that the inlet velocity and the outlet velocity are either pointed directly into a surface or directly out of a surface, giving you the situation where if they are pointed directly together in the same direction, you can simply take the magnitude of the vector, positive, and if they're pointed opposite, negative of the magnitude of that vector, of that U velocity vector. All right, so we know how to calculate U dot N now, so that helps us. So now we're going to go back to finding the answer to these. So we're looking here. We can figure out all of our U dot N's because all of our velocities are perpendicular to our surfaces, so they're all going to either be plus the magnitude or minus the magnitude of the velocity. That sounds good. We have U values. We don't have U values at B yet or W values at B, but we know the U values at A. So we still have some velocities to find, and we see we need to find all the velocities to make this work. So here we go. Here's the A velocity. The A velocity is simply 0.6 in the x direction. This is meters per second. and 0 in the y direction, 0 in the z direction. So the A inlet is just going in the x direction. We saw that earlier. So there's W is equal to 0, as we said, and that means that we're going to have no z term on the A surface. For the outlet, we also have no z velocity, W equals 0. We have an outlet velocity that we do not know yet because we have not calculated it. We know the fluid has got to come out of that outlet because we have 2 inlets. Obviously, the fluid can't just stay in the nozzle forever. So it's going to have to come out, but we don't know how fast it's coming out yet. But we do know it's coming out in a direction that does not involve z. It's coming out in a perfectly x direction based on the diagram. The z force, therefore, it has 0 components coming from surface A and coming from surface outlet. The only z force is going to come because of surface B, because that surface B is the one that had the fluid entering the nozzle at an angle upward in z. So that's going to contribute a z force. All right, we need still U and W at surface B. We have not calculated that. We also need U at the outlet. We know the density is 1,000 kilograms per meter cubed because we were told it's water, and we always use 1,000 for water. All right, at point B, we can calculate the U velocity and the W velocity. So we know the U vector here. We know the angle relative to the x-oriented, the x-axis. So we can calculate that the x component of velocity is 3.4 meters per second, which is the magnitude of the U vector, which you were given, times the cosine of pi over 3. So that's going to give me 0.5 for the cosine value. 3.4 gives me an x velocity, a U velocity of 1.7 meters per second at the B surface. For W, it's 3.4 meters per second, the magnitude of the U velocity, times the sine of pi over 3. The sine of pi over 3 is 0.866. Therefore, I have an upward positive z velocity of 2.94 meters per second. I always use a common sense check here. Is this pointed correctly in the positive direction? Is positive z velocity right? It is. Z is up, and the fluid is clearly going up to some degree. So I am expecting a positive z velocity, and I am expecting a positive x velocity because the fluid is traveling slightly positively in the x direction. I never trust the signs for sine and cosine. I always use a common sense check to make sure that these are correct, that magnitudes look good, but is it actually positive? I also always check to make sure the magnitude of this vector is equal to 3.4. So I always square this, add them together, and take the square root. It takes me like very little time, and it's a very good check to make sure I didn't screw something up. If it should come out to 3.4, and it does come out to 3.4. So in this case, I've got my two velocities at the B surface, my x and my B velocity. For the outlet, I need to find the velocity. I know it's only in the x direction, but I have mass in equals mass out. Okay, so here's my mass in, mass out equation. I have rho times the air inlet of the inlet velocity in the x direction here, which is perpendicular to the surface, and then times the area A. And for the other inlet, I have rho times the magnitude of the velocity because it's traveling in the direction of perpendicular to surface B times area B. So these are my two inlets. This is also magnitude. It just happens that the magnitude of this, because it has only an x component, is the same as the x velocity. That's going to equal the outward x velocity times the area of the outlet times the density. The densities are all going to cancel here, so I can just ignore them. It's just going to be an area velocity relationship. I need to calculate all three of my areas. Here they are, pi d squared over 4 for all three gives me these three different areas. So I have the areas of all of my surfaces, and then I can plug in my 0.6 times area A, 3.4 times area B has to equal the outlet velocity times area at the outlet. When I turn the crank, I get an outlet velocity of 45.8 meters per second. So really, really going fast. Not surprising, we have a pretty big areas for the inlets, a very small area for the outlet. We have two inlets and only one outlet. Not surprising, we have a very fast outlet velocity there. All right, so now I can plug everything in. I'm plugging into my force x equation. I have my 0.6 meters per second. That's my little u here. This is my rho. This is my u dot n, right? So it's in the opposite direction, because for this surface, A, the velocity is going that way, the outward normal is going this way, because my nozzle goes like this. And so there's my outward normal. They are opposite, so I get a negative 0.6 here. And then this is the area for A. That's area of A right there. So that's my answer for that part. Same thing here. This is my U component of the B velocity. This is my density. This is my U dot N at the B surface. So I've got the magnitude of U times, dotted with n. Here I got u dot n gives me magnitude of u with negative sign again, because once again, my velocity and my unit normal are pointed in opposite directions as this fluid enters the nozzle. So that gives me a negative 3.4 here, but only a 1.7 here, because this is actually, sorry, this is not, yeah, this is u. This is the x velocity at the surface, and it's not 3.4, it's a lot less. It's only 1.7 for u, but this is the amount of fluid entering through that surface, and that is negative 3.4 meters per second. So that's going there, and then that's times the area of B, which is right here. Finally, I have the outlet. At the outlet, I've got the 45.8, still the same density. 45.8 again, this is u dot n. Now they're aligned because the u and the n are both pointed in the same direction. So they're pointed in the same way, so that's a positive number, not negative like these inlets. Outlet is positive, and then the much smaller area. When I add all of that up, here are my numbers, negative 2.29, negative 7.28, and then look at this one. Wow, really fast. That's because it's a squared relationship, so a change in velocity has a huge effect, has a squared relationship effect on the answer. When I add that all up, I get 362 newtons in the positive direction. So this is, again, you're seeing a lot of force coming because of this high speed flow coming out. So that means that in order to hold this steady, I am expecting to have to push this thing in the positive x direction, because I have a strong jet of fluid leaving the nozzle from the front. That's going to push it hard backward. So in order to hold this stable, I need to apply 360 newtons of force to the nozzle to keep it from shooting backwards. So again, a common sense check on your sign here. You have a lot of fluid leaving really, really fast from here. That's the big force. These forces are really small. 2.2 newton, 2.3 newtons, 7.3 newtons. Those are really small going the other direction. It's this 371 newtons right there that's really driving this problem. That's pushing the thing hard, backward. So that's where you're expecting to see a number of pushing forward to keep it still. In the z direction, here's my w value at the B surface. Remember, the B surface is the only one that has a z contribution. There's my density again. Here's my u dot n. Of course, again, this is negative because it's entering the surface. It's the magnitude of u, which is 3.4. So that's there. And then you've got your area B, and that gives you at 12.6. You got to push it a little bit downward, 12.6, to keep it from popping up. And that, again, makes sense. If you've got fluid pushing up in here, getting shoved up in there, you're expecting to have to push it down a little bit to keep that nozzle steady as that fluid tries to push it up. I will say I like this solution because it really emphasizes the mathematics of these equations here. Again, I'll go back to the equations that are so important. These equations right here are the equations that allow you to calculate these forces. These are the forces equations. Being really able to apply this will really, if you get good at this, that will make you a good engineer. Like really understanding this u dot n, why this is u, why this is w, why this is built the way it is. That will help you to be great. So I really like coming from here. There is another way to do this problem that Griffin Kelly pointed out. I think it's a good solution too, and it does work. If you just treat this component as giving you an x force, this component gives you an x force, and this component gives you a force. If you just ignore the fact that it's w and x right now, just treat it as fluid coming in along this direction, calculate the total amount of force that would be pushing in this direction, and then divide that force into an x and a z component and add it to these forces you calculated here. That also works. It's a clever solution. It's a good solution, but it doesn't really take advantage of, it doesn't help you to master really using this equation, which is, the more rigorous and more generalizable solution. This is technically accurate for any problem that has this kind of momentum conservation, whereas this is taking advantage of a clever observation. It's a good observation that that you can treat this as its own kind of axis here and break it using cosines and sines. At any rate, say this is true. Now remember, this momentum conservation for control volume, it is an approximation. It assumes that all the velocities are uniform and the density is uniform in the entire inlet, across the entire inlet and across the entire outlet. That is not generally true. Fluids generally do not have uniform velocities when they're near walls, but for nozzles, high-speed nozzles, actually, this is quite a good approximation. We'll be studying this later in the class, exactly, how the real fluid profile coming in and out of tubes and pipes. But for high-speed nozzles, it is reasonable to assume that the velocities are approximately uniform across the entire inlet and outlet. So this is a valid, good engineering solution. So there you go, and that's how you solve it.